Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to this lecture of Embedded Software Design and Validation. Today we are going to discuss about a data flow model of computation. Now we will be following the same textbook, Introduction to Embedded Systems, a Cyber Physical Approach, and to talk about data flow model of computation, we first understand that whatever we are going to talk today, this is about some asynchronous model of computation. Now, by dictionary meaning, we know that asynchronous means not in time, right? So, why they are asynchronous, why the components are asynchronous? There may be two main reasons. One, maybe there is no synchrony in the events. Another thing is that the reactions of multiple subcomponents, they are dependent in terms of data flow. That means, in short, let us say there are multiple actors, let us say two actors A and B, and they are dependent on the data flow, like whatever data A is producing as an output, maybe that should be taken as input by this actor B. Okay. So, that is why this type of model of computation, when data flow is a major issue, major cause of dependency, that type of modeling we are going to discuss today. So, when reactions are dependent on one another, the dependence is due to the flow of data rather than to the synchrony of events. Okay. Here, as we have already mentioned, if a reaction of action A requires data produced by a reaction of actor B, then reaction of A must occur after the reaction of B. Okay. So, this is in this scenario how to model the computation that we are going to discuss. Now, when we are talking about data flow principles, there are two main points to discuss. One is, in the data flow model, the signals providing communication between the actors are sequences of messages. Okay. So, from one actor to the other, there is some sequence of messages, and each message sometime we will be denoting or we will be mentioning as token. Also, these kind of models, they are associated with two types of functions. One is one actor function. It is basically mapping the input sequence to the output sequence, depending on their type, depending on their transition conditions given. Along with that, we will talk about some firing functions. So, these firing functions, they basically map a finite portion of the input sequence. Here we are not talking about the whole input as we are considering in the actor function. In firing function, we are considering the finite portion of the input sequence that to be mapped to some part of the output sequence. So, let us take a few examples to understand how we are actually defining actors, what we mean by actors in this context. So, here is one example actor. This relation gives the actually input output mapping of this example actor, where we can see if we take some message sequence x1, x2, x3 and so on. So, the output we are expecting as AX1, AX2, AX3 and so on. So, that means to define these kind of actor functions, we need input output of course, also Vx that we have also discussed in our previous lecture, the type of inputs that is getting handled by the input port, and also for this particular actor we need one scaling value, scale actor. We are considering this as we can see all the inputs are getting scaled by this factor A, and so this is one parameter of this scaling actor. Okay. So, as we are discussing about the actor function, so we understood this is the mapping, this is this input to this output mapping is basically the target of this actor function. Along with that, we have the firing function that is acting on parts of the input sequence. For example, first the actor function, when it is firing, it performs one multiplication, that means multiplication with the scaling factor, and then it is taking that part of the input, we can mark that as token, and that token is getting scaled by the scaling factor, the parameter decided by this or stored in this actor. Okay. So, another example actor maybe will be quite useful later on. So, maybe we can mark it as delay actor. This is nothing but we are adding some delay to a particular input sequence. Let us consider this is the input sequence x1, x2, x3, concatenation of few tokens, and the output of this delay actor will be adding this delay parameter d with this input sequence. So, here this actor, if we this actor function or actor target, if we go deeper and if we break the actor function, we will get two firing functions, d1 and d2 we are mentioning here. So, for the first part, the first firing function, what it is doing, there is no requirement of input for this firing function. It is basically producing an output sequence of, here we have considered length 1 or any length depending on the type of delay we are trying to add up to this input sequence. In the second firing rule requires one input token and is used for all subsequent firings. That means the second firing part, it is taking the first token, maybe second token and so on, and it is just appending this output to the final output of the actor. So, this way the functionality of the actor or the function mapping of the actor can be divided into subsequent firing functions. Okay. So, we will be it is important to understand, because this token, this firing of a function, etc., these terms we will be using quite frequently in this discussion. Okay. Now, if we see this delay actor with in a form of FSM, whatever we have discussed before, FSM form. So, this can be one representation of this delay actor. See, here we have considered two states S1 and S2, and S1 to S2 based on certain when certain GERD condition is getting satisfied. For example, let us say we have considered that we will produce the delay for certain global clock tick. Okay. So, we have considered some global clock, we are measuring the ticks, and when some particular number of ticks are passed, maybe this condition is getting satisfied. Then we are setting the output y equal to d, the output value is getting set with this delay parameter value, and there is a transition from S1 to S2. While this FSM in state 2, it is basically setting the output, it is taking the input tokens exactly from the sequence and setting this output value. So, at the first part this delay value is getting set, and the second part and the consecutive iterations whenever this FSM in S2, it is basically considering the input tokens and setting them as part of the output. Okay. So this may be one FSM representation of this delay actor. Okay. So that way, if we now, as we have divided the whole actor operation in firing functions, according to that firing functions, we can associate or we can decide the states, and we can decide the state outputs and the state transition conditions. Okay. So as here the firing function D1 is associated with state 1 and D2 with state 2. Based on that, from the firing function we have actually identified the states and then gradually the state transition conditions. Okay. So that way these firing functions are actually defining the actor outputs finally. Now we will discuss, gradually we will discuss about more complex data flow realizations, but to start with we will discuss few problems to be handled in this data flow or this type of model of computation. The first thing we need to understand that there is a dependency of data, okay, and these firings are asynchronous. So whenever if we consider this type of communication, whenever A is firing, the output is getting consumed by B. But there are two requirements. First of all, whenever A is firing, there is no guarantee B is also consuming at the same time. Another thing is that the way the outputs, the amount of output A is generating, there is no guarantee B is also consuming in the same rate. So the number of tokens and the number of rates in which the tokens are generated from the sender side, there is no guarantee in the same rate or in the same number the receiver will also consume the token. Okay. So what is the necessity then? If the rates are different or the consumption is not happening at the same time, there must be some buffer present in between. There must be some buffer. So that's why it is written, since the firing of the actors is asynchronous, token sent from one actor to another must be buffered, so that as and when required, this receiver side can consume that token. Okay. It needs to be saved until the destination actor is ready to consume it. When the destination actor, this one fires, now we know the meaning of firing. It is consuming the input and it is doing the necessary function mapping. It can consume one or more tokens. After being consumed, a token may be discarded. So the question comes here, as we are trying to understand, how to ensure that the memory devoted to buffering of tokens is bounded. That means it may go to an unbounded situation. Maybe huge tokens are getting generated from the sender side A, but B is consuming very less. So it can go to a very huge unbounded situation where the memory you are keeping for this buffer, that is getting exhausted. That means the number of tokens generated and not consumed by the receiver side is already filling up the buffer, and still A is consuming some more tokens to be stored, but there is no place in the buffer. Okay. So this cascade composition we have already discussed, that if A can fire at any time and B is not consuming at the same rate. So what we have to do for a successful modeling in this kind of data flow, we need a scheduling policy. That means there should not be any token lost. Whatever tokens getting generated extra, other than the tokens getting consumed, when the tokens are getting consumed by the receiver side, they are getting discarded, that is fine. But before that, it should not happen that some data is getting lost. Okay, some token is getting lost, to be specific. So we need a scheduling policy that deliver bounded buffers. So there must be some bounding on the generation or in the storage part or in the consumption part. Okay. So we will say we will see in detail that in which form we can actually decide these scheduling policies. This is not the only problem. The second problem is there is a possibility of date lock in this type of data flow setup. Why? Just understand with a simple example. Let us consider this one, the feedback models we have discussed just in our previous lecture. So here this actor A or actor C, they are producing some output that is getting consumed by B. Again, A is dependent on the output coming from B. Okay. So if we just consider that, we think that in terms of data flow, basically B is dependent on some input data, B is dependent on A for some input data, whereas A is also dependent on B for some input data. Now this can happen in any feedback scenario. Here also, here you can see this B output is acting as an input to this actor A. Again this A output is acting as an input to this B. So if this situation is not handled properly, then there is a possibility of complete deadlock. That means, deadlock means A will be waiting for the input coming from B and it can never complete its own task. B will be also waiting for some output coming from A and B is also waiting for A, and there is a complete deadlock. Okay. So the deadlock occurs when there are cycles and the directed loop has insufficient tokens to satisfy any of the firing rules of the actors in the loop. So if we think simply, these A or this A, they are having some firing rules and they are waiting for some tokens coming from B or vice versa. So here some delay actor or some specification of input tokens can help to solve the matter. Like for the initial steps, if we define that some actor, some extra actor will produce or will decide some input tokens to A, so that A can fire its transition. Once that is done, the first level output will get produced and that will in turn satisfy the requirement of firing in B, and B will produce the output. Once that output is getting produced after the initial delay, from the next time take or next time onwards, next iteration onwards, B can produce output that can get consumed by A. Okay. So this is a delay and deciding of input sequences properly. It is a necessity to handle the deadlock scenario. Okay. So for general data flow models, it can be difficult to tell whether the model will deadlock and whether there exists an unbounded execution with bounded buffers. So whenever we are modeling a scenario, a complex scenario, a general system, we are taking to our model, we are mapping that with some with our model of computation. It is important to handle that deadlock. Also, it is important to handle this bounded unbounded execution with our bounded buffer scenario. And for that, as we were mentioning, we need some scheduling policy. And to understand that scheduling policy, we need to have some constraints. We will see how defining some constraints can answer this or can solve this problem, can make this problem decidable. That means we can, based on this constraint, we can actually analyze whether our model will go to some unbounded direction or there will be any possibility of deadlock. Okay. So, when we are talking about constraint scenario, we are basically talking about synchronous data flow. Okay. Synchronous data flow is a constrained form of data flow where for each actor every firing consumes a fixed number of input tokens on each input port and produces a fixed number of output tokens on each output port. That means, if you see, just check this diagram. Here this A to B communication, the number of tokens can be generated are not unbounded now. Now we know we have a constraint that A can produce maximum M tokens at a time and N can actually consume maximum N tokens at a time. Okay. So, SDF actor A produces M tokens when it fires and actor B consumes N tokens when it fires. Now, it may happen that we are telling at a time it is A or B, they are consuming or producing M or N tokens. We can consider over a particular time interval, A can fire QA times and B can fire QB times. Then effectively the number of tokens will be produced within that time interval will be QA into M, and for actor B it will be QB into M. So, to have a balance in the full situation, we need to have at least QA into M equal to QB into N. So, that will give a balanced scenario. Okay. So, that is why here comes a scheduling policy or the concept of schedule, that when we are modeling, we are deciding the time interval, we can actually decide or actually control according to our requirement that how we are deciding this QA and QB. That means how many times within that interval this QA can happen. That means how many times actor A can fire, how many times actor B can fire. Okay. So, and based on that our simple scheduling policy can be A fires repeatedly QA times followed by B or some other arrangement. Okay. And we can repeat this sequence without exhausting the available memory. So, if we handle this way, we schedule the firing and the number of tokens this way, we can prior know that okay, whatever bounded buffer limit I have, within that this all the tokens can be handled and there will be no loss of tokens. That means that in turn will confirm that there will be no loss of data. Okay. So, let us see that with some example. Consider we are the values M is equal to 2 and N is equal to 3 and actor A is firing 3 times and actor B is firing 2 times. So, what is happening at a particular interval if we consider 3 into 2 6 and this is also 3 into 2 6. So, 3 times A is firing and then 2 times B is firing. There may be an alternate schedule AB. Let us see how it works. So, first for the first firing A is generating 2 tokens. In the second firing A is generating again 2 tokens and then B is consuming 3 tokens. So, we are keeping that as minus 3. So, 1 token is left. Again A is firing, again there is 2 tokens. So, now effectively we have 3 tokens in total and now B is actually consuming that 3 tokens. Okay. So, that means at each of the time if we consider the first and the second scheduling, we see for the first one we need to store 2, then 2, then 2, total 6 maximum. Actually, at least we have to keep the buffer length in such a way that it can hold at least 6 tokens at a time. Whereas if we see this one, the buffer length we can design in such a way that maximum 2 tokens to, if it can hold, that is enough. So that's why this lateral schedule, this one is having one advantage, that it requires less memory. Okay. So when we are talking about this data flow computations and we are thinking about deciding about the buffer length, so and the constraint, whatever we are putting on the buffer, it will also control which way we are deciding our scheduling policy, and vice versa. The way we are deciding the scheduling policy, if we do not have any constraint on the buffer length, or up to a certain extent, I must say, then based on our scheduling policy we can actually choose our buffer length. But choosing and deciding this buffer length and having a policy in sync, that is important to avoid any unbounded scenario to happen. Okay. And we are also assuming here B files as soon as there are enough tokens, rather than waiting for A to complete its entire cycle. So especially for the second one, A is not completing its entire cycle, but B can consume whenever as many tokens it requires for the initial firing that it is getting. Okay. So this is one example scheduling. Now we will see some other arrangements. Here we have 3 actors acting together. So what may be the type of the balanced equations? So since there is one, that means one actor, one token getting produced, so QA into 1, that is QA is equal to QB into 1 QB. The next one is to 2 into QB plus 1 into QC, and 2 into QA, this one 2 into QA and 1 into QC. So these are the balanced equations. Now if we try to solve this equation, the least positive integer solution of these equations are QA is equal to QB is equal to 1 and QC is equal to 2. So here also the schedule will be QA is equal to 1, so A, QB is equal to 1, so B, QC is equal to 2, hence C. Okay. So these can be, so this is not restricted to 2 actors. Whenever we are adding or increasing the number of actors according to their token generation, actually we can form these kind of balanced equation. We will try to solve this balanced equations and we will get the numbers that how we can actually generate the schedule. Okay. Now we will see a small modification where these kind of scheduling, if we do not take care properly, can lead to some inconsistent situation. Okay. Now just we are making a small change here, instead of 2 the outputs getting produced, let us consider a scenario where just one output, this output token is getting generated by B. So if we just follow the same way, now my balance equations are QA into 1 is equal to QB into 1, QB into 1 is equal to QC into 1 and 2QA equal to QC. So these are my balanced equations. Now if we try to solve, the only solution we get will be QA is equal to QB is equal to QC. That means there is no non-zero solution exists for these balanced equations, and these may lead to inconsistency, and an HDF model that has a non-zero solution to the balanced equations is said to be consistent. Okay. So, consistency is sufficient to ensure bounded buffers. That means, if we are deciding the scheduling policy in such a way that we are getting some non-zero solution here as per the tokens getting generated, tokens getting consumed, as per the number of actors we have, as per the numbers of firings we are considering all these facts. Okay. If we are getting a non-zero solution, we can ensure that we can handle the problem with some bounded buffers. Okay. But this is not a solution to the deadlock problem. Okay. So, there may be some unbounded execution and that may lead to some deadlock. Okay. So, this is whatever with this balanced equation we are checking or we are trying to handling, that is sufficient to ensure that this unbounded execution we can actually deal with some bounded buffer, but this is nothing related to deadlock. Okay. So, for deadlock what we need to do, we will see in the step. For this deadlock we have to check if there is some loop. Here we have taken one example of feedback loop, and we have to additionally, we will go by the same way, we will form the balanced equation, but we have to see if there is some requirement of this initial tokens. Otherwise, if these initial tokens are not here, considering the bounding we have applied on the output or inputs of B, still there is a possibility of deadlock. Why? Because as we mentioned before, this A is waiting for some tokens for some outputs coming from B. Now, since at the initial step we are allowing this initial tokens to be produced by some actor, and that initial tokens are getting consumed by A and it is producing the output that in turn drive the firing of B. Now, see the number of initial tokens we are going to generate, that is also, or we are going to provide, that is also bounded or controlled by the binding we are applying on these outputs or inputs. For example, see we know that we need 3 tokens to fire the requirement of A. So, if we are initially giving just 3 tokens, what will happen? Let us say not 4, we are giving 3 tokens. So, if we are giving 3 tokens, okay, it will generate 3 outputs 3. From there 2 will be consumed by B, and at the first level B will generate 2 tokens as outputs. Now, what will happen now? These 2 tokens are coming as inputs to A, but still A requires 3 tokens to fire. So, again there is a deadlock. A is waiting for some more tokens, but B that is not getting produced from B. B is again waiting A to complete to generate some more tokens so that it can start its next fire. So, again that is a deadlock equation. So, based on these bounds phi 2 etc., whatever we are defining, these initial tokens should also be calculated. That is why we have given this 4 tokens, where the first phi will get consumed by the first firing and the last one, maybe the 4th one, will get consumed along with these 2 tokens generated by B in the next iteration. So, this way the balance equations, they are not only sufficient, we have to consider these initial tokens to guarantee there will be no deadlock. Okay. And after that the balance equations are formed, so that is 3QA is equal to 2QB, 2QB is equal to 3QA. Again the less positive integer solution will be 2, 3, and then we are scheduling this in this way. But that is to mention that if there was no loop, then only handling with this balance equations are sufficient. But when we are having this loop into account, we have to also check if an initial token is required or not. Okay. So, this way we can handle both. We can actually handle some unbounded execution with some bounded buffer. Along with that, we can actually handle this feedback loop, and we can actually sort out the deadlock problem. Okay. But there is still one limitation of this whatever we have discussed in SDF, that is SDF cannot guarantee or cannot handle the conditional firing. By conditional firing we mean that here we are considering, okay, A is generating some output token and B is consuming it, that is it. But when will A produce the token and when not? That comes under the conditional firing, and this part cannot get handled by SDF. That is why we are discussing about some dynamic data flow where these conditions are appended, conditions are considered. Okay. So, where an actor fires only if a token has a particular value. So, such conditional firing is supported by a more general data flow model of computation known as dynamic data flow. Here we will be talking about two basic actors. One is the select and one is the switch. First understand the actors and then we will go and understand how these actors are actually realizing any full construct. So, this is the select actor. Okay. So, the select actor has three firing rules. Initially, it requires one token on the bottom input part. Okay. In this input part, there is this black triangle you can see. So, this part is basically Boolean in nature. So, whatever input is coming with, that may be true or that may be false. Okay. If the type of input is true, this top left part, that is getting enabled. So, what will happen if there is any token, that token will wait till the input, proper input is coming here, that is a condition given. If that true input is coming here, then only if any input token present, then this transition can get fired. That means the output input output mapping can take place from this part, top left part. On the other hand, if the type of input here is false, F, then if some input token present in this part here, then this transition will fire. So, that means based on the conditional input we are giving in this line, in this path, that is basically controlling which part will get enabled, whether the top left or the bottom left, and based on that the output will get generated. Okay. So, this is the select actor. Okay. The type of that okay, initially it requires one token on the bottom input port. The type of the port is basically Boolean. So, the value of the token must be true or false. Okay. So, if a token with value true is received on that input port, then the actor produces no output, but instead activates the next firing rule, which requires one token for the top left input port, level T. When the actor next fires, it consumes the token on the T port and sends it to the output port. Similarly, okay, the same thing we have already discussed. If a token with value false is received on the bottom input port, then the actor activates a firing rule that requires a token on the bottom left input port, level F. So, here this part. So, this is how the select actor is basically working, and it is allowing the conditional firing based on the conditional value coming to this input port. Okay. The next actor is the switch actor. And the switch actor is actually doing the reverse. Okay. So, the switch actor, what it is doing, if some value is coming, some token input is coming, the switch actor is deciding in which part this input token will when there will be a if this input token is appearing and it is firing a transition, which part the output will go. So, whether that is this part or this part. So, again based on the value coming to this port, if it is true or false, based on that the firing output will go either to this part or to this part. Okay. So, this is basically the token on the left input port will be sent to either the true path or the false output port, depending on the Boolean value of the token received on the bottom input port. Okay. So, this is switch is basically just doing the reverse of the select actor. Now, we will understand that using this two, this select and the switch. Okay. How we can actually realize this if then else construct. Okay. That is one important part of this data flow model of computation, right. When we are considering data flow and when there are multiple actors attached, so which path the data should flow. So, that decision making if then else construct will be realized by this switching and selection. So, you can see that same switch and select are attached here. A is providing the input and B is some input stream. Let us consider, if we think in general scenario, we can consider this A is providing the data and this B is providing some control input, and these inputs are getting forked and it is actually activating these paths, these points of select and switch. So, first one is select. Okay. First one is the switch part, as we have discussed. First one is the switch part. So, this switch operation, switch actor, what it is doing, it is taking the data from A and it is checking what type of input is coming through this Y. That means Y is coming basically from X, X is getting forked to Y and this Z part. So, what is the value, whether it is true type of value or false type of value, based on that this value coming from actor A is taking that path. Okay. So, if Y is actually giving some true value, so this path is getting enabled. So, this transition will be there and the value will pass to actor C. If Y is giving some false value, then this path will get enabled and this value from A will come to actor D. Then after the outputs are getting produced from C and D, now we are actually selecting, hence the select actor is here. Based on the Z value, whether it is true or false, either this true transition or this false transition will get enabled and either the value from C or the value from D will come to actor A. Okay. So, this way we can see this if then else concept is getting handled or getting modeled by this select and the switch actor. Okay. So, with this understanding, now we will mention briefly a popular modeling technique of this data flow, and that is called Petri nets. Okay. That is named after Carl Adam Petri, who proposed this concept back on 1989. Okay. Now, in Petri net we have two types of elements. Okay. We have places, you can see in the circle and some tokens inside. and this is the transition. So what is happening? The places can contain tokens, input tokens. It may only one single place is shown here. It may happen that multiple places are connected for the same transition based on the requirement, what type of tokens we need. Maybe these tokens are getting generated through multiple actors, and those are holding these different places are holding those tokens, and they together are responsible to fire any transition here. Okay. So, a place can contain any number of tokens depicted as black circles. So, only a single one shown here, but it may happen multiple tokens are present. A transition is enabled if all places connected to it as inputs contain at least one token. Once a transition is enabled, it can fire the transition, and the output tokens will get generated and it will be placed in these output places. Okay. And this is called the marking. The state of the network, call its marking, is a number of tokens present in each place. Maybe it is an input place, maybe in some scenario it is the output place, maybe this output place is acting as the input to some next level transition. So, this is called the state of the network, and this is called the marking of the network. Okay. Now, we will see few important properties of PET-VNets. This is the image reference mentioned for this particular two images I have taken for related to PET-VNet properties. The first property we are going to discuss about synchronization and concurrency. So, first the synchronization means, you could see here, the tokens should be present in all the related input places, so that, and they will be in sync. Like, it will not happen that if some places are not having the token, then this transition E1 cannot take place, the firing cannot take place here. So, that means these places should be in sync, at least in case of holding the tokens, so that this then only the firing can take place. And once the firing is, so that is the property of synchronization, okay, required for PET-VNet, the tokens, input tokens to be placed or to be present to start or fire any transition. The second one is the concurrency part. Now, this concurrency means that this transition has taken place. Okay. After that, the output tokens, it may happen that there is only a single path. Let us consider there is a single path and the output token is actually going there and getting placed in some output place there. Or it may happen that these tokens are actually getting placed in multiple output places and starting some concurrent again path of executions. Like again, maybe this token is getting for some next level of transition and some output token is getting generated and so on. Okay. So, that comes under synchronization and concurrency properties of PET-VNet. Okay. So, synchronization we are talking about this input side, and the concurrency we are talking about once the output places are getting filled up with some tokens. Okay. Then finally, another property, important property, is how this concurrency can lead to some non-determinism. So, when we are having, let us say, multiple tokens in this path, and it may happen these output place is connected to multiple concurrent paths, multiple concurrent firing to execute. So, there may be a possibility that it may lead to some non-determinism, that there is no guarantee that when the token is present, which one to trigger, which transition will it trigger. Okay. So, if that may happen when any input token place is connected to multiple paths, multiple concurrent paths. Okay. So, this while designing or defining petvinet, so this non-determinism should be handled carefully, and there should be a specific definition, that a specific constraint declaration, that how many tokens to be taken to this path, how many tokens to be taken this path, whether that is sufficient with whatever we are defining that these input place can hold, etc. So, all these things should be taken care of to avoid any kind of non-deterministic behavior in the network. Finally, we will take one example how we can actually model a practical scenario with the petvinet. Okay. So, here we have taken one example of two concurrent programs running concurrently, this program A and program B, and they are with mutual exclusion requirement. What do we mean by mutual exclusion? Maybe A and B, they are sharing some resource, some critical resource, and when they are making any change on the critical resource, one program is making any change on the critical resource, the other program should wait until the another program is completing its modifications on the critical resource. So, in short, whenever these programs are in mutual exclusion, they can access the critical resource one at a time. Okay. And that we are defining by this mutex token. So, let us understand this. For program A and program B, this is the transitions defined, these are the transitions, and these are the token places. So, this A in the mod A is in its critical section if there is a token in A2, okay, and this B will be in its critical section if there is any token in B1. But how can we get some token in A2 or B1? Now, observed, if there is some input token in A1 and some mutex token, and program A is consuming these mutex token, then only these transition can happen, and then only some token will come to A2. That means A is in it's holding the critical resource, or A is in its in mutual exclusion step. Okay. So, now once A is already consumed this mutex token, this place is holding only a single mutex token. So, there is no token left. So, that means now this in the program B side is B is still trying to access that critical resource. Still what will happen? This, let us say B2, this token is already present, but still this mutex token is not there. So, this transition will not get fired, and that is why the B1 and A2, both the places cannot have token at the same time, and that ensures that program A and program B cannot access the same critical resource and at the same time, and hence the mutual exclusion will hold good. Okay. So, this is the basic idea, this is the scenario we are modeling with petvinet. Now, observe, when this A2, this is having the token, it is basically enabling this transition, and now this mutex will have another output token. Once this token is present here, this can now act as the input here, and when B2 is present, the token in B2 is present, together they can actually, the program B can actually enter in the mutual exclusion. That means these transition can fire. So, this is how once A is releasing the mutex token, then only B is actually consuming this mutex token and it is entering in its critical section. So, this is the concept of mutual exclusion, how it is modeled, and we have seen how it is modeled with this petri nets. So, just check in the slides, each of the two programs has a critical section. In the model program, A is in its critical section if there is a token on place A2, this one, this is A2. Program B is in its critical section if there is a token in place B1. The job of the mutual exclusion protocol is to ensure that these two places cannot simultaneously have a token. So, that we have seen how it is getting ensured. So, if the initial marking of the model is as shown in the figure, then both top transitions are enabled. That means A1 and B2 both are having tokens, but only one can fire because there is one token in the place labeled mutex. Which one fires is chosen non-deterministically, anyone can fire actually. Suppose program A fires, after this firing there will be a token in place A2, we have seen that. So, the corresponding bottom transition becomes enabled, this one becomes enabled. Once the transition fires, the model returns to its initial marking. Now, we are having one in the mutex, one in the B2, and program B can enter in its critical section. So, this is the example we have seen how we can do this data flow type of modeling using this petri net actors. Okay. So, this is all about data flow modeling we have discussed today. Here I will stop. Next day we will talk about validation of models, what we mean by validation, why is it important in the context of modeling and design, and finally how to do this validation of different kind of models. So, that will be our next day topic. So, this is the main reference, the books and the images also taken mostly from the books. Only some petri net property related images I have taken from separate slides. So, that references are given in that slides itself. So, with this I conclude this discussion. Thank you.